We should go get one, and then we should finish it.
Yeah, that's an industrial accident.
But this one has
You know what? I wish I just identified which specific class of water gave you cancer. You know, wouldn't it be cool to know? No, I know it's all probabilistic, but what if there was just one that just sent you over the edge into cancer? You know? I really want to what a superpower that would be.
super. Then you can run your statistics off.
And naturally, when I'm already running behind schedule, it doesn't want to go into full screen mode. Okay. There we go. Sorry for the delay. It was for a good cause. I was preparing homework 6 in today's lecture and proofreading essays that were due today. But anyway. Is now my clicker not working? Or is it just really slow? It's just really slow. Okay. Woohoo! Covariance and correlation. What could be more exciting, I know. So, hopefully at least the first part of this, if you've ever taken statistics before, this will be a bit of a review. But it's worth knowing the properties just because they can pop up on exams and qualifiers and things like that. But say we have two random variables, mean mu x, mu y, variance is sigma x squared and sigma y squared, all of which exist. The covariance of x and y is defined to be just the expected value of x minus mu x times y minus mu y, usually denoted by sigma xy. And the correlation, again, hopefully you've seen before, is just defined to be the covariance divided by the square root of the product of the variances. And we say that x and y are uncorrelated if their covariance is equal to 0, or equivalently, if their correlation is equal to 0. Oh, a few properties of the covariance. If you take the covariance of a variable with itself, that's always just equal to the variance of that variable. You can see that immediately from the formula on the previous slide. The expected value of x minus mu x times x minus mu x, of course, just x minus mu x squared, which is the definition of the variance. Likewise, the covariance is symmetric, so the covariance of xy is equal to covariance of yx. And for any constant, the covariance of any other random variable with that constant is always equal to 0. That has to do with the fact that expected value of x minus mu x for a constant is always 0. And if you expand the formula for the covariance, you can see that it's also equal to the expected value of x times y minus e of x times e of y. The proof of that is fairly straightforward. I won't step through it. And if x and y are independent and the covariance exists, then the covariance of x and y is always equal to 0. The covariance can fail to exist. Well, the obvious example is if the expected value doesn't exist, that you could have two independent Cauchys, for instance, but they don't have a covariance because their expected values do not exist. And it's worth pointing out that uncorrelated does not imply independent. That if x and y are independent, then their covariance and correlation are always 0. However, the converse does not hold. That just because x and y are uncorrelated does not necessarily imply they're independent. The example most people use for this is that under certain setups, if you let y equal x or minus x with a certain probability, it's easy to show that the correlation between the two variables is 0, even though they're obviously highly dependent on one another. And you can also show that if x and y are random variables with variance, that is, at least their first two moments exist. That would not include the Cauchy, for example. The covariance of ax plus b, y, and z is just going to be a times the covariance of x, z, and b times the covariance of y, z. And variance of ax plus by turns out to be a squared times variance of x plus b squared times variance of y plus 2ab times the covariance of xy. Note that in this case we do not assume that x and y are independent. That we've discussed this formula in the past, that if x and y are independent, then variance of ax plus by would just be a squared variance x plus b squared variance y. You can see that's consistent with the formula up there, because if they're independent, then covariance of xy will be 0. But even if they're not independent, you can find the formula for the sum of the variances. You just have to take the covariance into account. And similarly, if you work out the algebra here, that if you take the correlation of ax plus b and cy plus d, you take two variables and take a linear transformation of both of them and take correlation. The correlation doesn't change, with the exception that it could possibly go from positive to negative if one of the things that you multiply one of the variables by is negative and the other one's positive. Oh, a couple other theorems involving the correlation. It's always between -1 and 1, a property you've probably seen before. We're going to prove it here in a second. And it's exactly equal to 1 if and only if the one variable is a linear function of the other variable. That is, you can write y equals ax plus b for some a and b. And the correlation will be 1 if this a is greater than 0, and it'll be -1 if this a is less than 0. So how do we prove this? Well, let's first convert x and y to standardized variables, or z-scores they're sometimes called. That we do that by just subtracting off the mean and dividing by the standard deviation. We do that just because it makes the proof a little bit cleaner, that the correlation between x and y will just be the expected value of x twiddle times y twiddle. So, obviously, x twiddle minus y twiddle squared is greater than or equal to 0 for all possible values of the random variable. So, if we expand that out, then we end up with the expected value of x squared plus the expected value of y squared minus 2 times the expected value of xy. Based on the way we set this up, expected value of x squared and the expected value of y squared are both equal to 1. We end up with 2 minus 2 times the expected value of x twiddle y twiddle is greater than or equal to 0, which of course implies expected value of x twiddle y twiddle less than or equal to 1, so the correlation is less than or equal to 1. Similar logic for if we take x plus y quantity squared, that's also always positive. We solve it, we end up with -1 is less than or equal to correlation. And the only way that we can get exact equality in either of the two above expressions is if probability y twiddle equals x twiddle is exactly 1, or it's the probability y twiddle equals minus x twiddle is exactly 1 sort of thing. Make sense before I go on to the bivariate normal? Okay. Oh, bivariate normal distribution. That given some number -1 less than or equal to rho less than or equal to 1, rho, as you're probably already guessing, is just going to be the correlation coefficient. The bivariate normal density is defined to look like the following. You see it's similar to the normal density that we're familiar with, but it has a rho term in the middle of it. It's now 1 over 2 pi times square root of 1 minus rho squared times e to x squared plus y squared minus 2 rho xy divided by 2 times 1 minus rho squared. And if you want to do some funky integrals and things like that, then you can show the marginal distribution of x is normal 0, 1, as is the marginal distribution of y, and the correlation of x and y is rho. And the conditional distribution is also kind of annoying to calculate. That involves change of variables and integrals and things. But if you calculate it out, then you end up with a normal with mean rho times x and standard deviation 1 minus rho squared. Likewise for the conditional distribution of x given y. And this, again, to illustrate the point that at least some things I teach in this class have purposes other than helping you pass qualifying exams, that this formula actually, I ended up using it in a program a while back for imputing missing data. The basic idea is, well, it was actually a multivariate normal distribution, which we'll come to a bit later, but basically I was trying to say, okay, say that we're given a set of data that we observe, and we want to compute the expected value of the data that we didn't observe. Well, we can use this formula or the analog of this formula for the multivariate case to calculate what the mean and variances of the things that we didn't observe should be, so that we can make simulations from those distributions and so forth if we're willing to assume the whole thing is multivariate normal. And it actually becomes kind of an interesting research area, because to do this, you need an estimate of the covariance matrix, which is very hard to do if the dimension of your data set is high. But I'm starting to digress way beyond the scope of this class. But if that gets you excited, then come talk to me someday and we'll geek out. But anyway. And you may recognize that these means are just the regression lines of y on x and x on y, respectively. And we can also have a bivariate normal distribution with means not equal to 0 and standard deviations not equal to 1. So if you take the standard bivariate normal that I described in the previous slide and do a transformation mu x plus sigma x times x, that'll give it some mean and some standard deviation greater than 0, likewise for y. Then we end up with this kind of horrible expression for the bivariate normal density. My recommendation is don't even try to memorize that. Here soon I'll give you the matrix form of this that is not only easier to remember, but it works for greater than two-dimensional data. But if you actually expand out all the matrix stuff, you end up with something that looks like this. And you can show, once again, the marginal distribution of that bivariate normal that I just showed is mu x sigma x squared. Marginal of y is mu y sigma y squared. In general, this bivariate normal is you just take a normal with some mean and some variance and a second normal with some mean and some variance, and you just assume they have some correlation between the two. Under that quite general setup, you have the bivariate normal density that I described on the previous slide. And the correlation between x and y is rho, as I said earlier. Conditional distributions, once again, if you work out, they're normal and look something like what I'm showing here. And again, that's just equivalent to the regression line. Any questions about the bivariate normal before we shift gears to multivariate distributions generally? All right. Oh, and I guess there were a couple more bullet points here. You can take linear transformations of ax plus by, and you get this. Cool. Okay, so we've discussed bivariate distributions thus far. Now we'll consider general multivariate distributions that say you have some n-dimensional random vector. By convention, it's defined on the Borel sets in the hyperspace Rn. Again, don't worry about the details unless you're planning to take 760 someday. And in general, if the variables are discrete, if each of the individual random vectors are discrete, then we have a discrete, or each of the individual random variables are discrete, then we have a discrete random vector. If they're continuous, then we have a continuous random vector. And if x is discrete, then to find the probability that x equals some value, or x, or more generally that x is a subset of some Borel set or some set of real numbers, you just take all the possible values of x corresponding to that A and sum over them. That if you want to find like the probability that x is less than or equal to 3 and y is less than or equal to 4 and z is less than or equal to 5, well, you just sum over all possible x's where x is less than or equal to 3, all y's where y is less than or equal to 4, all z's where z is less than or equal to 5, and just plug it into your PMF and add them all up. Continuous case, it's the same principle, just messier because you have to integrate over the region corresponding to the things that we care about, and hopefully you won't have to do this very often because I don't know about you, but usually doing complicated double integrals is not my idea of fun. And we can define marginal distributions and conditional distributions just like we did in the bivariate case. The marginal PDF can be computed by integrating or summing over the joint PDF or PMF over all the other possible coordinates. And I guess, well, before I bring that up, that it's worth pointing out here that in the multivariate case, you have x1, x2, up to xn. You can define the marginal of x1, the marginal of x2, etc., but it also makes sense to talk about marginals on some subset of the variables. You could talk about the marginal of x1 and x2, the marginal of x1 and x3, the marginal of x1 up to xn minus 1. Any possible subset of the individual coordinates can give you a marginal. And similarly, you can take some subset of the x's and condition on some subset of the other variables to get a conditional PDF, and it's the same sort of ideas we did in the bivariate case, that you just take the joint PDF of the variables of interest divided by the ones that you're conditioning on. Oh, an example of this that we discussed briefly a few weeks back is the multinomial distribution that, say, let n and m be positive integers, and there are n different possible categories of the outcome with probabilities p1, p2, up to pn, all summing to 1. And I probably should have redone this example to make n the number of trials rather than the number of possible categories to be consistent with what we did with the binomial. But yeah, to be honest with you, I was putting this together at like 4 in the morning and I just decided I was too tired. If I'm feeling motivated, maybe I'll change these slides once I get back to my office. For the time being, just bear with me and try not to get too confused. In this case, then the random variable x1 up to xn has a multinomial distribution with m trials and cell probabilities p1, p2, up to pn. If the joint distribution looks like m choose x1, x2, up to xn, times the probability of the p's each to the appropriate power of x, which can be written as m factorial over the individual factorials down at the bottom. And the proof that this is a PMF is called the Multinomial Theorem. If you look at this for a second, if n is equal to 2, that is, there's only two possible outcomes, success and failure, then you'll see that this PMF is exactly the same as the PMF of the binomial. Multinomial theorem, it's theorem 4.6.4 in Cassel and Berger, that say m and m are positive integers, and A be the set of vectors such that the sum of their non-negative integer components is m. That is, that you take some set of things such that they're all integers that sum up to m, and each one of them is greater than or equal to 0. Then you can show that p1 plus p2 up to pm to the power m is that sum right there, which should hopefully look familiar or look similar to the formula for the PMF of the multinomial distribution that we saw on the previous slide. And so if p1 plus p2 up to pn all sum to 1, then 1 equals that sum on the right-hand side, so the PMF sums up to 1. Woohoo. For n equals 2, that's just the same as the binomial theorem that we proved on an earlier homework. For n equals 3, then the summation looks like that. Kind of messy, but you get the idea. Hopefully it's fairly doable. And you can show in this case the marginals are also multinomial, that if you take the marginal with respect to any one variable, that turns out to be binomial with m trials and probability of success p1. If you take the marginals with respect to, say, some subset of 3 variables, then that works out to be multinomial with m trials and probability of success p1, p2, and 1 minus p1 minus p2. And you can also show the conditionals are multinomial, that, for instance, if you want to find the conditional distribution of x1 up to xn, given that xn equals little xn, then that's multinomial with number of trials equal to m minus xn. Makes sense because we know that the final outcome happened xn times. There's a total of m minus xn trials left to be accounted for, and to make the probabilities of the rest sum up to 1, you just divide each of them by 1 minus pn. And you can also compute the variance and covariance of these things, and you end up with the variance of each individual xj is just m times pj. 1 minus pj makes sense. That corresponds to what we saw in the binomial case. Or the covariance between an xj and xj and xk turns out to be minus m times pj times pk. Any questions about the multinomial distribution? Okay. Moving onward, multivariate independence. That, say you have x1 up to xn random vectors with joint PDF or PMF, f of x1 up to xn, we can calculate the marginals for each of these individual variables, as I discussed earlier. And then x1 up to xn are said to be mutually independent random vectors if for every possible x1 up to xn, the joint PDF or joint PMF is just equal to the product of all the marginals. Once again, consistent with what we did in the bivariate case. And we can generalize the theorem that we discussed earlier with respect to the expected value of independent random variables, that if you take the expected value of x1 times x2 times up to xn, or in general, any function of g1 of x1 times g2 of x2 plus times gn of xn, that's just the product of the individual expectations. We proved that in the bivariate case. The proof in the multivariate case is completely analogous. And likewise for moment generating functions slash characteristic functions, if x1 up to xn are all independent with corresponding characteristic functions, and that's a typo, that should be up to phi of xn, not up to phi of x2, then, and you let z be the sum, then the characteristic function of z is just the product of the characteristic function of the individual variables. In particular, that if all of them have the same distribution, I guess I forgot to write the punchline down at the very bottom, if they all have the same distribution, then the characteristic function for z is just the characteristic function for any one variable raised to the nth power. And seems like a dumb little side note, but that's actually crucial to proving the central limit theorem, as we'll see in a couple weeks. So here we just randomly insert specific characteristic functions for a bunch of different distributions. I'm not sure why Mike Wu or Armin Schwartzman or whoever created these slides decided to insert this right here, but you know, this is useful for doing homework, so make a note to yourself that it's in the middle of this lecture. Anyway, any questions about multivariate independence before we go to multivariate moments in the last little section? Okay. And yeah, this section is not covered in a ton of detail in Cassell and Berger, unfortunately. If you bought the textbook by Goot, it's chapter 5 there does a better job of covering it. Otherwise, pretty much everything that you'll need to know for this class will be in these slides, but this stuff is worth knowing because, as I said, multivariate normal is something that knowing its properties can come in handy for a number of real-world problems. Well, anyway, first of all, defining multivariate moments, say we have some random variable x1, x2, up to xn, then the mean vector mu is defined to be a vector just consisting of expected value of x1, expected value of x2, so on down to expected value of xn. Nothing shocking there. You can also define the matrix of second moments defined to be the expected value of x times x transpose. That if you work out the matrix math, you end up with expected value of x1 squared, expected value of x2 squared down the diagonal, and each off-diagonal element is just expected value of x1 times x2, expected value of x1 times x3, etc., where hopefully the pattern is fairly obvious. In my experience, that's not something that one computes or cares about very often. What one does care about is this variance-covariance matrix, which is defined to be x minus mu times x minus mu transposed, which is, of course, just the expected value of x minus mu times x minus mu transposed, which, if you write it out, becomes variance x1, variance x2, variance xn in the diagonals, and the covariances are in the off-diagonals. You can also standardize this to get a correlation matrix, which also gets used sometime. And like I say, this is maybe I'm showing my personal biases here about the types of things that I care about when I'm not teaching 660, but at least one of the 3 most important things that I care about when I'm teaching 660 is one of the, at least, 2 of the most important things that I care about when I'm teaching 660 is one of the, at least 2 of the most important things that I care about when I'm teaching 660 is one of the, at least 2 of the most important things that I care about when I'm teaching 660 is one of the, at least 2 of the most important things that I care about when I'm teaching 660 is one of the, at least 2 of the most important things that I care about when I'm teaching 660 is one of the, at least 2 of the most important things that I care about when I'm teaching 660 is one of the, at least 2 of the most important things that I care about when I'm teaching 660 is one of the, at least 2 of the most important things that I care about when I'm teaching 660 is one of the, at least 2 of the most important things that I care about when I'm teaching 660 is one of the, at least 2 of the most important things that I care about when I'm teaching 660 is one of the, at least 2 of the most important things that I care about when I'm teaching 660 is one of the, at least 2 of the most important things that I care about when I'm teaching maybe I shouldn't say the hottest areas in statistics. One popular area of statistical research right now is just good ways to estimate this thing, particularly when you have lots of variables and not very many observations. That one of the problems in statistics generally, is going a little excursus here, is that an estimate of a variance typically has high variance. It's something that you don't really think about very often, but if you just have a bunch of data and you compute the variance of that data and you want to like find a confidence interval for your variance, there are ways to do it. And if you do it, you'll be surprised at how huge that confidence interval is, because it's hard to compute a variance exactly. That you don't really appreciate how nice the whole t-test thing is, because if we didn't have the fact that you take something, subtract the sample mean, divided by sample variance, and it has a nice distribution, then in principle what you would have to do to find a confidence interval for anything is, well, so the confidence interval for the mean depends on the variance, but there's uncertainty in your estimate of the variance, so to find the confidence interval for a mean, you would need the confidence interval for the variance, but to find the confidence interval for the variance, you do need the confidence interval for the variance, you get the idea. The fact that we have a nice distribution, we just take x minus sample mean divided by standard deviation to avoid all that, is actually one of the most remarkable things in statistics, since it's one of the first things taught you, and in an intro course you don't really think about it. But in problems where we don't have that nice distributional theory, where we actually care about the structure of this covariance matrix and need to make inference based on that, that thing is really difficult to compute accurately. So figuring out ways to compute it accurately is kind of a cottage industry right now. And if anyone's geeky enough to get excited about this, come talk to me and we'll have exciting conversations. If not, you can just like tell them about the weird professor you have for 6-6 who got really excited about covariance matrices. But I just want you to know that some of these things, like once you get done with qualifying exams and start to do research and things, that there are things in here that people still care about. And note that after that whole long-winded thing about covariance matrices, note that it's always symmetric, just because covariance of x1, x2 is equal to covariance of x2, x1. So, in general, if you transpose it, you end up with what you started with. It's symmetric. And like the bivariate normal case, if you have mean vector mu x, mu y, your variance covariance matrix looks like sigma x squared, sigma y squared, rho times sigma x, sigma y. And so you can write the joint density of the vector x as 1 over 2 pi times the determinant of the variance covariance matrix times e to the 1/2 x minus mu transpose times sigma inverse times x minus mu. And if you remember a formula for the distribution of the multivariate normal, that's the one that you will want to remember, as you'll see here in a slide or two. This is the density in the bivariate case. See that the one in the multivariate case is almost identical to this. In fact, I think the only difference is that rather than 2 pi at the far left side, it'll just be 2 pi to the n over 2 in general. It's sometimes, if you're like me and took linear algebra a long time ago, or like me and took like a rinky-dink linear algebra course from some podunk college in northern Utah and never took anything higher than that, this matrix math gives you a headache. So if you struggle with that, then you're in good company here. So yeah, I really wish I had taken more linear algebra when I was in school. I'll just say that to anyone who feels like they haven't taken enough of it. I get by, but I find that I have to look up everything. So this type of matrix math gives me a headache sometimes, and just do the best you can, and when in doubt, take another linear algebra course. And given some random vector with mean mu and covariance sigma, then for any random not random, this would actually be a fixed vector, c1, c2 up to cn, then you can define a random variable y to be a linear function of these x's. You just multiply c1 times x1 plus c2 times x2, etc., etc. And fairly easy to show that if you do this, then the expected value of y is just the vector dot product or inner product, it's sometimes called, of the scalar c with the mean vector mu from the original data. And the variance, if you're actually good at matrix math, you can compute that to be c transpose times sigma times c. And for the people like me who never really got enough background in linear algebra, or if you have taken linear algebra and just need a quick refresher, that an n by n symmetric matrix is said to be positive semi-definite or non-negative definite if for every c transpose times lambda times c is greater than or equal to 0. And it's said to be positive definite if for every vector like that you get something strictly greater than 0. And the reason why we care about this sort of thing is the positive definite matrix is invertible, it has a positive determinant, and all of its eigenvalues are positive. The covariance matrix is always positive semi-definite, and in general it's always positive definite as long as none of the variables are perfectly correlated with one another. That the only way you can get positive semi-definite is if one of the variables is a linear combination of the others, so that it has less than full rank. So, for instance, if you can also do multivariate linear transformations. The previous slide, or 2 slides ago, gave the formula for, say you have a multivariate random vector and you want to convert it to a scalar by multiplying it by taking the inner product with some scale, well, some constant vector and the random vector, that will give you a scalar. You could also take a set of random variables and or a full random vector and transform it to another random vector by letting each y be some arbitrary linear combination of the a's. And so, using matrix and vector notation, you may recognize we can say this is just equivalent saying letting vector y equal matrix A, where A is the matrix consisting of all those individual A11, A12, etc., times random vector x, where A, as I just said, is that thing there. And the change of variables formula that I taught you earlier still works here, that the Jacobian of this transformation is just going to be the original vector A itself, so the determinant of the Jacobian is just going to be the determinant of the original A. And the inverse transformation, of course, will be x equals A inverse times y, and the determinant of A inverse is always equal to 1 over the determinant of the original matrix. So the multivariate normal, as I said before, it's exactly the same as the formula for the bivariate normal that I gave you a few slides back. The only difference is at the far left-hand side, the 2 pi is to the power n over 2 rather than to the power 1. Makes sense in the bivariate case, n equals 2, so you ended up with it to the power 1. And this works for a multivariate normal distribution with any set of parameters mu and sigma. So, in particular, you can show that the vector mu in this expression is just equal to the expected value of the random vector x, and the matrix sigma is precisely the variance-covariance matrix of x, defined to be x minus mu times x minus mu transposed. And so, how do you construct these variables and show that such a thing can actually exist? Well, let's say that we start with a bunch of IID normal 0, 1 random variables, that it's easy enough to find the joint density of those things, that since they're independent, we just multiply all the marginal densities together. We end up with e to the minus sum from I equal 1 to n zi squared over 2 pi to the n over 2, end up with e to the minus z transpose times z divided by 2 over 2 pi to the n over 2. So far, so good, I guess. So now let's take a linear transformation of those variables, that we multiply this random vector z by some transformation matrix A, and then add some mean vector mu. Well, then we can find the inverse transformation with some linear algebra. That's just A inverse times x minus mu. The Jacobian is precisely equal to A inverse, and the absolute value of the determinant of the Jacobian would just be 1 over the Jacobian of the original A. So, plugging all that into the formula, we get that the joint PDF of x is e to the minus x minus mu transpose times sigma inverse times x minus u divided by 2, all over 2 pi to the n over 2 times the determinant of sigma square rooted. And it's easy enough to show that the expected value of this x is mu, and the variance-covariance matrix is sigma, that if you're curious about matrix manipulations here, basically what it boils down to is, if you've had a good course in linear algebra, then you know that when you have like A times Z in parentheses transpose, that turns out to be you transpose each thing inside the parentheses but reverse the order. As you'll recall, matrix multiplication is not commutative, so the order of the multiplication does matter. We have A times Z, so we reverse this order and transpose both of them, Z transpose times A transpose. We end up with A times Z transpose times A transpose. End up with A times the expected value of Z times Z transposed. Well, Z was defined to be multivariate normal with mean 1 and all variance is 0. The expected value of Z times Z transpose is just the variance-covariance matrix of Z, which is of course the identity. So we end up with A times A transpose, which is just the definition of the variance-covariance matrix for sigma. And aside from the theoretical value of showing that these multivariate normals actually do exist and that it makes sense to talk about them, that if you wanted to simulate multivariate normal random variables, I mean, nowadays there's an R package that will do this for you. It might be built into standard R, I forget, but if you don't have a way to simulate it directly, you can just simulate it using matrix multiplication given a bunch of normal 0, 1s, the way I just described. Is there a question?
So, sorry, you said Z was the multivariate standard normal?
Yeah. That was the way we defined it on the previous slide, that said the individual z's be normal, IID normal 0, 1, so their joint distribution is a multivariate normal where all the means are 1 and all the covariances are 0. All the means are 0, all the variances are 1, all the covariances are 0. Sorry. Okay. So, some properties of the multivariate normal distributions. If x and y are jointly normal random variables, then x and y are independent if and only if they are uncorrelated. As I gave the example I gave earlier in class today, in general, independent implies uncorrelated, but the converse is not true. It's possible for two variables to have a correlation of 0 even if they're not independent. But if they're jointly normal, that can't happen. The only way they can be independent is if they're also uncorrelated. And likewise, if you have a bunch of jointly normal random variables, they're mutually independent if and only if they're pairwise uncorrelated. That, once again, in general, uncorrelated does not imply independent, and moreover, pairwise independence in general does not imply mutual independent, but both of those things are true in the case of the normal distribution. If a bunch of jointly normal random variables are pairwise uncorrelated, then they're all independent of one another. And if x has a multivariate normal distribution, then you can show that all the marginals are normal, all the conditionals are normal, and take any vector of constants and multiply it by the random variable x. That will be normal as well. And yeah, I think that's everything I had to say about multivariate distributions today. Any questions about any of this? I apologize for the fact that I'm behind on homework grading and responding to emails and pretty much everything right now. I'm going to try to catch up in the next 2 days. So if you've emailed me and I haven't responded, I'm not ignoring you. I just ran out of hours in the day even when I didn't sleep.